Guys, welcome back. Today we're going to be talking about work and energy principle. So, from our previous videos, we know that kinetic energy is equals to 1/2 mv squared, right? Now, if this doesn't sound familiar to you at all, I suggest you to go back to our videos and check it out. And we also know that work is equals to force times distance, right? So now, these two are going to be very useful to this work energy principle. So now, all that the work energy principle tells us is that, let's switch it up here, that net work is equals to the change in kinetic energy. Now, remember that net work just means the total work done in the system. Here is as well. So we can say that this is also to force times distance. Now when we combine those two equations, we have force times distance is equals to the change in kinetic energy. And further developing on that, remember that change just means final minus initial. So that means kinetic energy final minus kinetic energy initial. And that gives us our force times distance. And now this is a very, very useful equation in physics because now you can find the force needed to stop something, or if you apply a force over a distance, how much does the velocity change? Because remember, this breaks down even further, as in kinetic energy is again 1/2 mv squared. So this will be 1/2 nv squared final minus 1/2 mv squared initial is equals to our force times our distance, right? And then it's going to even break further. Remember that force itself is mass times acceleration, and you can just do a lot of things with this formula. But let's do an example based on this. So this formula right here is probably one of the most useful ones when it comes to first semester physics, which just derives from the work energy principle, which is work is equal to the change in kinetic energy. All right, so now based on this, let's do a real life example. The numbers are made up, so just bear with me. So now let's talk here logistics. So for example, let's suppose you have a street, and then there's a car. I'm really bad at drawing, guys, so I apologize for that. So I'm just going to say that this is a car or a box. Let's just say something like that. Just call it a car. Actually, let me try to. Now it has wheels, so now we can call it a car, I guess. And a door or a window. All right, now it's a car. So a car is traveling at 20 meters per second. And then over here you have an old lady crossing the street who just, didn't notice that there was a car coming at 20 meters per second. And you notice her when you're 10 meters away from her. You're driving a car that's 800 kilograms heavy. And now you're like, oh my God, there's an old lady. And you slam on your brakes, and the force that your brakes can apply is going to be 5,000 newtons. All right? So now that's the force that your brakes apply on your car. So now I want you to find if this distance is enough distance, not time, but distance for you to stop and not run over this person, or if unfortunately that person, will end up at the hospital. And you'll probably end up in jail. I don't know what your country's policy is, and I don't know. But anyway, moving on. So now we're going to use our very useful force times distance equals to change in kinetic energy. So now, do we know the force? We do. The force of the brakes that's stopping us. So now we're going to plug that in. So 5,000 newtons, right, times our distance that we want to find out is going to be equals to, notice here the mass is the same. The mass here is the mass of the car because that's our mass, or that's our object that's moving. Because this car, remember, is traveling towards this person. This person just crossing the street vertically, I guess, here. So it's like coming from here to here. So they don't move as our car is moving. So remember from our previous videos as well that you treat them separately. So we're just treating the horizontal axis right now. So then 1/2 mass comes out, and then you have velocity final squared minus velocity initial squared as well. All right, so now what we're gonna do here, our mass, we know what our mass is. It says 800. So now let's just go ahead and plug numbers. I went ahead and plug in the force here, my bad. So 5,000, right, newtons times our distance is equals to 1/2, or 1/2, 800 kilograms times our velocity final square. What is our velocity final square? Do we know that? Well, what did I ask initially? So you see her stop, and you see her crossing the street, right? So you want to stop the car, right? This is our key word. Stop means that our final velocity is going to be 0 meters per second. All right? So anytime you see the word stop, that means 0 meters per second. So now we're going to plug in 0 squared, which we all know 0 squared is 0, or if you didn't know, now you do. Now minus, what was our initial velocity? Well, we're traveling at 20 meters per second. We have to square that, don't forget. Now, when we do, we get negative 400 meters per second, meters squared per second squared, times 800 kilograms divided by 2 right here. So this just becomes 400 eventually, right? Equals to 5,000 newtons times D. So now, when we do the math, we find out that D is actually negative 32 meters. Now, you may be wondering, what does that mean? Like, what does the negative 32 mean? And it just means that you need 32 meters to stop. You need 32 meters before you end up at rest. So for example, you end up right here, right? So you need 32 meters before that. So you need 32 meters to stop. All right, so we only have 10 meters to stop. So that means that at the time we impact this person, we're still going to be going pretty fast, because in total we needed 32 meters. So then if we do plus 10 meters, we end up having a deficit of 22 meters. So we are missing 22 meters to stop before we hit that person. So unfortunately, this person would die, and you would suffer the consequences or of your actions. So now the interesting thing is going to be that we're going to be able to follow this when in our next videos when we do momentum. That's kind of, I'm sorry, really bad spelling. Not spelling, but grammar. So when we do momentum, we're going to be able to follow this problem up, and we're actually going to find out at the moment of impact how far actually we ended up pushing this person away from where she was initially. So again, real life situations, when you see a car that hits someone, I hope you never do. It's sad, but if you do, and now you know how to calculate how, the impact, how far they will go and stuff, which is very interesting. Again, so look up for, wait for our next video on momentum follow-up. I think it's going to be great. And so, yeah, I hope this video really helped you, and I'm trying the new black background, so please give me your feedback. If you guys like it, if you guys don't like it, just let me know in the comments. Remember to like us on Facebook and follow us on YouTube. And contact us if you need any video or any concept explained, even if it's advanced physics. One of our team members, he's actually doing research in galaxies, kinetics, and it's really cool. So yeah, just let us know. Until next time, good luck studying.